Hello, everybody, and welcome to Chapter 13 in Dynamics. This is Professor Algara with a video to cover a lecture about the topics that we'll be having in this chapter. So chapter 13 is one of the easiest because it has a foundational knowledge that is similar to what we had in statics when we were doing equations of equilibrium, sum of forces in the x and the y direction. The only difference right now is that we'll be covering movement, right? We'll start considering mass and acceleration as a way to study movement. So the first thing is just remember the three, Newton's law. You've been very familiar with this from physics one, statics, and all of this. But let's just read through it. So the motion of particle, right, of a particle is governed by Newton's three laws of motion. The first law is when a particle originally at rest or moving at a straight line at a constant velocity will remain in this state if the resultant force acting on the particle is zero. You're familiar with that one. Sum of forces equals zero. The second law is the one that says that the resultant force of the particle is not zero. The particle experiences an acceleration in the same direction as the resultant force. This acceleration has a magnitude proportional to the resultant force. And the third law, which is mutual forces of action and reaction between two particles are equal, opposite, and collinear. All right? Action and reaction. The second one, the sum of forces equals to mass and acceleration. And those kind of things as a foundational knowledge is very important that we remember that before we get into this topic. Okay? So the first and the third laws were used in developing the concepts of statics. We did that in statics. Newton's second law forms basics of the study of dynamics. So mathematically, Newton's second law of motion can be written as forces equals to mass and acceleration, where F is the resultant unbalanced forces acting on the particle, and A is the acceleration of the particle. The positive scalar m is the mass of the particle. All right. So that's everybody's very familiar with this. So now we need to study something that is quite important, right? And people usually get confused between mass and weight when treating not only dynamics problems but also from statics. I've seen that all the time. It is important to understand the difference between the mass and the weight of a body. Mass is an absolute property of a body. It is independent of the gravitational field in which is measured. The mass provides a measure of the resistance of the body to change the velocity. As defined in Newton's law, mass is equals to F over A, but this comes from forces is equals to mass times acceleration. The weight of a body is not absolute since it depends on the gravitational field in which is measured. Weight is defined as mass times gravity. All right, don't forget that because people usually get confused with that. When you are treating these problems, you have to remember this. So in the SI system, international system, or the metric system as we call it, weight it's equals to mass, gravity, and usually the unit for this is newtons as the gravitational force on the surface Earth is equals to 9.81 meters per second square. All right, when you multiply that times kilograms, then you will get newtons. And don't forget that it's very important that we know the units that we're talking about. And when we go to the IPS system, mass is expressed in slugs, and then the total weight is expressed with the following units. All right, it's very important that we know how to treat both exercises because you might have both cases. Equations of motion. All right. So far, we've been just refreshing everything. The motion of a particle, like we said, is covered by Newton's second law, relating the unbalanced forces on one side, and then the acceleration that as a result of these unbalanced forces happen. Okay. Fr, it's a resultant force, which is a vector summation of all the forces involved in a movement. Okay, as you can see here, from here to here. To illustrate this equation, you have to think about um, a particle in which has two forces as you can see here, this small particle, right? And by using the vector sum, you can get your resultant force. All right. Like I said, it's very important that we know that there are forces in the vector form. And as a graphical way of having the resultant force, this is what we will have. And all these forces, when they are expressed into one single picture, when you have all of those forces acting into a particle, is when we have something called free body diagram. And I'm pretty sure we've been doing that a lot in statics and physics, but in case you forgot. And then now I'm going to introduce you to something new, that is the kinetic diagram. In this kinetic diagram, you have all these kinetic forms of energy that are involved with the movement. Okay, and that's why you might need your kinetic equations. I'm just telling you a small secret that is coming after a while. All right, so now we're going with the equation of motion for a system of particles. So basically, and like I keep referring to statics because it's the same foundational knowledge. You will have all of these masses and accelerations involved with each one of these particles for internal forces. Those are equals if you sum all of those masses to the mass in the center of mass, called G. All right. So the equation of motion can be extended to include systems of particles, like a combination of different ones. This includes the motion of solids, liquids, and gas systems. As in statics, there are internal forces and external forces acting on the system. So you know the difference between them, and I don't have to remind you of that. But using the definition of mass equals the sum of all of the masses and the total mass of the particle, and something important, which is AG, or the acceleration of the center of gravity, or the center of mass, sorry, then the equation can be rewritten as this. All right, but for that to happen, you will have to have the information of the location, all of these particles in order for this to work. So key points, okay? Newton's law is a law of nature, okay? Experimentally proven, not the result of an analytical proof. Mass, a property of an object, is measure of the resistance to change the velocity of the object. Weight depends on the local gravitational field. Calculating the weight of an object is an application of these formulas, and don't forget that, because you will be working with weight a lot, it's not the mass. You have to multiply the mass and the gravity in order to get the weight. Unbalanced forces cause the acceleration of the object. This condition is fundamental to all of the dynamics problems. So how can we put like a procedure together in order to do all of the exercises? And this is quite important. Again, very similar to statics, super similar to statics. So first of all, you need to establish an inertial coordinate system. You know, rectangular, normal, tangential, or cylindrical will be used. But what matters here is that you establish your x and y properly, or tangent and normal. It doesn't matter how you call it, but what matters here is that you establish your coordinate system properly. Something might be positive for you, and then the sign will tell you whether you were right or not. It's exactly to what we had in physics. That's the nature of physics, okay? Then once you have that established in your head, you have to draw a free body diagram showing all of the external forces applied to the particle. All right? You have to resolve the forces into their appropriate components. So once you have your x and y, if you have a force that is not aligned with the x and y that you determine, then you will have to resolve the forces into those components. Then after that, and this is new, you have to draw a kinetic diagram. And this is useful because at least it's showing you where the movement is going, okay? It's usually one vector or one arrow with mass and acceleration. And usually that helps you visualize the different problems that you will have and the different unknowns that you have on your problem, so you can start utilizing the equations that you have at your disposal. Then after that, we need to apply the equations of motions. And once you have that, you will realize how many unknowns you have. And based on that, just based on that, you might have to use your kinematic relationships, the relations, the ones that we learn in chapter number 12. equations with the position. For example, final position is equals to, you know, initial position plus BOT plus 1/2 of acceleration t squared, and you have the other one, the second, and the one that it's the result of the other of the first two. If for any reason you don't remember this, just go back to the video in chapter number 12 so you can remember this, okay? So now let's start, as always, to do one exercise to kind of show you as a little, as little as it is, just what we mean by that. And I had a doubt whether to include this exercise or not because I think everybody is familiar with regular free body diagrams, but just because I wanted to show you the kinetic diagram and what it is and the things that we usually take into consideration for these kind of problems, I wanted to share this exercise with you. So a 25 kilograms block is subjected to force equals to 100 newtons. The spring has a stiffness of K equals to 200 newtons per meter and is on a stretch when the block is at A location. The contact surface is smooth, which means we don't have friction force. We only need to draw the free body diagram and the kinetic diagrams when the block is equals to S 0.4, which is, this is the initial state and this is the final stage, and that's what they're asking you to do. What would be the plan? So at first we need to establish a coordinate system that will be given by us. Then we need to draw the free body diagram showing all of the external forces, and then we need to do the kinetic diagram in order to show the inertial forces. So the thing is here, before I start throwing numbers, we need to know the data that we have and the calculations that we need to do before doing this. So at first, the mass was given because it's kilograms, right? So you need the weight. You need to multiply that by 9.8, meters per second squared in order to get your weight in newtons. You need to do everything in force dimensions. So then after that, you have to realize that you were given with a K. Remember that the force of any spring will be equals to the K of the spring, which is the universal constant for springs. And then that has to be multiplied for the elongation that the spring had. Delta S is quite important because then you need to see what you have, the state that you have in your picture, right? You have at t equals 0, and then this is t equals x seconds, okay? What you need to realize here is that you have a little triangle. And this triangle has one side equal to 0.3, the second side it's 0.4 because that's what they're asking you to do. Therefore, this side will be 0.5. And if you need to know exactly how much it elongated, then you have to realize that delta S is equals to 0.5, which is the final, minus 0.3. So delta S is equals to 0.2, and you need that to calculate the force due to the spring. And this is just physics and statics, all right? I'm just looking at the data that I have because I know I will need that. So you can do those calculations beforehand because you are going to use them. Do you need them for right now? You don't, because all they're asking you is the free body and the kinetic diagrams. Okay, but it's very important that you realize that you will need that. Okay, so okay, free body diagram, and we also need the kinetic diagram. And remember, this is when S is equals to 0.4. That's when the spring is completely stretched. So you all know how to make a free body diagram. We have the normal force going up. We also have the weight going down. Then we have the force that was moving or pushing the box. And as a result of that, we have the force of the spring, right? And like I said, you can always see that this was 3 and 4. So therefore that would be 5. You all know what I mean by that, right? When you're not given with the angle, then you have to specify that. And obviously remember that force of the spring, as I said, is delta S that multiplies Ks. And that's it. That's what you need in order to get that thing. And this is equals to your kinetic diagram. The kinetic diagram, remember, is the result of all of these forces, and that will, you know, basically translate into mass and acceleration. So in this case, it's equals to mass of A and acceleration. And that's all. This is all they were asking from us. Just the free body diagram of the blocks of the block when S was equals to zero point 0.4, which is when this was stretched. So this is the equivalent as to sum of forces is equals to MA. Okay. So then I added something much better drawn for your references. But just keep in mind that I follow the steps I gave you in the previous slides. It's as simple as that. So now we're moving into rectangular coordinates. And like I said, very similar to what we had in the past. So the equation of motion forces equals to ma is used when the problem requires finding forces, especially forces perpendicular to the path, accelerations, velocities, or mass. Remember that unbalanced forces cause acceleration. We have said that too much. Three scalar equations can be written from this vector equation. The equation of motion, being a vector quantity, may be expressed in terms of the components as you are familiar, x, y, and z. All right, or the scalar forms, whatever. Each one of those can be written as that. All of the forces in one direction plus all of the forces in the other direction plus all of the forces in the third direction, because it's a 3D environment, it's equals to the mass that multiply to each one of the components of the acceleration, in x, y, and z. All right, very straightforward. So the procedure for analysis, and I can stress this enough, but your free body diagram is very important. It's critical. If you don't realize and you don't understand this right now, then you will have problems moving on, because you're just learning how to, deal with these problems when now all of these forces are not equal to zero. So it's very important that you understand what's happening in the movement, so you can place all of these forces into the free body diagram, and then you can analyze that, you know, in order to determine your equations of motion. It is often placed in a case where 2D it's placed 2D equations x and y. And when that happens, it's very important that you divide these analysis into the proper x and y's is when that is given. All right. Then kinematics, like I said, it's very important that when you have more unknowns than equation, you find the proper equation you need in order to find, the unknowns that you have. Most likely, you will need one of these equations, the kinematics that we cover in chapter number 12, to determine how much the acceleration would be, and then you can plug that value into that. And let's just make sense with an exercise. There's no better way. So in this particular case, you have a motor that is connected to a cable with a constant acceleration, just that 20 kilograms move distance equals to 6 meters in 3 seconds, starting from the rest. They're giving you mu k, which is related to frictional force, as you know, dynamic frictional force, and they're asking us for the tension developed in the cable. And again, same thing. We use a free body diagram, then we use sum of forces equals to ma, and then we use kinematic equations if they're needed. Then after that, we can apply, all of our equations in order to get the results we're looking for. So I wanted to show you just right on. If we take a look at this, the first step is to determine your x and y. All right. In this case, X and Y has been moved with the same inclination you have in the exercise. And why is that? Because when you establish your X and Y, you will realize that the tension, the normal force, and the frictional force, they are moved 30 degrees just as your coordinate system. And that will make it easier for you to work with them, since the only force that you need to convert into the coordinates will be the weight, because it's the only one going down. And if you have that information, right, then based on that, you can place your equations and do your sum of forces with no problems. And again, this is the free body diagram, and this is the kinetic diagram. And it's very important that you place them both so you can understand exactly what needs to be done in order to solve this exercise. So just by looking at it, I know that I will have to do a sum of forces in the y direction, and it's positive for me going that way. And this is equals to, and this is one question, is this equals to ma or is it equals to zero? So the answer to that question is pretty simple. Do you have movement in the y direction? You don't, right? You have a frictional force, you have a normal force, you have contact, so therefore this will be equals to zero. The only movement right now, it's in the x direction, as you can see in your kinetic diagram. All right, with that being said, on the y direction I only have the normal force. Sorry, normal force. Sorry, we'll just start over. I have the normal force going up, and then going down, I have the weight, which is 20. And don't forget to multiply the weight by 9.81. And then you are going to use the inclination that you have in here in order to find the components of the weight. So this has to be multiplied. This has to be multiplied by the cosine of 30, and this is equals to 0. From here, I can get that the normal force will be equals to 169.9 newtons. Okay, and now after that, you can now do the following equation. Why do you need the normal force? Well, you know that the frictional force or the kinetic frictional force will be equals to mu k that multiplies the normal. So now that you have the normal, you can plug that value into this in order to get your frictional force. And why is that important? Because when you do the sum of forces in the y direction, you will need this. I'm sorry, in the x direction. So if we do that, sum of forces in the x direction, going positive with the movement, this will be equals to ma. As I do this, I will have tension minus 0.3 times the normal force minus the weight that is going down, multiply, well, weight, and this weight will be multiplied by the sine of 30, and then this will be equals to mass acceleration. So now when you see this, you know that this is given because you have the normal force. This is also, you can calculate that because it's the same one as 20 times 9.81 times sine of 30. You have the mass, but you don't have acceleration. You don't have also the tension. So what can you do then? You know, and that's when the question comes. What should I do? Should I go with kinetics, or do I have any other equation that I can use? In this case, obviously the answer is very simple. I will use kinetics in order to complete my exercise, right? So I have that S is equals to BOT plus 1/2 acceleration t to the square. And I know because in the statement of the exercise they were telling you that it started from 0, which means your BO is 0 and then your initial position is also 0, but they're telling you that the final position is 6, and they're telling you that the t is equals 3. So I can easily find the acceleration then, because I will plug these values in. So this is 6 equals 2, BO is 0, and this is 1/2 of acceleration that multiplies the t to the square. Solving for acceleration, you get that acceleration, it's equals to 1.333 meters per second square. And now you can take this value and plug it into the equations of equilibrium in order to get t minus 0.3 multiplies the normal force minus 20 times 9.8 times the sine of 30. This is equals to the mass, which in this case is 20, and multiplies the acceleration, which is 1.333. Therefore, the tension it's equal to, according to my calculation, should be approximately 176 newtons. And if this is not right, please just check my calculations, shoot me an email and I can fix it. But that's the result I got so far. So the process or the procedure repeats itself as you move on. It's very similar. You always have to do your free body diagram, your kinetic diagram. You have to establish your x and y, and usually you establish that based on the amount of forces that are coincident with that x and y. So your calculations will be easier because you will have to decompose the forces that are not coincident with this axis into the proper axis, and when that's happening, it just involves more confusion. Then after that, you do your sum of forces equals to mass acceleration, and then a kinetic equation will be needed, most likely, in order to find the third unknown. All right. So if you have any questions, like I said, you can shoot me an email. Now we're moving to another case. It's very similar, guys. So we study curvilinear movement in chapter number 12. So it's very important, and I think it's very important that we also cover the normal and tangential coordinates when they are needed. When a particle moves along a curved path, it might be convenient to write these equations that we've been studying, equations of motion, in terms of normal and tangential coordinates. And I want to stop myself right now because what you need to realize, and this is just another x and y, but we're just using another coordinate system very similar to what we had before. And what we need to consider here is just the direction for each one of them. So the tangent components are always tangent to the path, and the normal components are always pointing to the center of this curvilinear path. All right, and this is important because we have acceleration involved, two components for acceleration, and then we have, the change in the position, the change in the velocity when we're studying all this movement. The normal direction always points toward the path center of curvature. In a circle, the center of curvature is the center of the circle. Everybody knows that. The tangential direction is tangent to the path, usually set as positive in the direction of motion of the particle. So the equations of motion, as you know, always and all the time is always equals to mass and acceleration. So it is convenient to rewrite these equations in terms of normal and tangential. And the book give you a binomial or another axis that will replace the z-axis when it's needed. Okay, so here the sum of Ft and Fn are the sums of the forces components acting in T and N, which is tangent and normal direction respectively. These vector equations will be satisfied provided the individual components of each side of the equation are equals, resulting in two scalar equations which are equals right here. Sum of forces in the tangential axis are equals to mass and tangential acceleration, and the sum of forces in the normal direction are equals to the mass times the normal acceleration. Since there's no motion in the binomial normal, then we can say that the sum of forces in that binomial will be equals to 0. Tangential and normal acceleration were developed last week. Okay, we had a very interesting lecture posted on YouTube, and if you have questions, you should email me. We spent, I think, like 15 minutes just developing these two equations. So I will refer to that video if you have questions, but as always, I can answer questions on the email or on Zoom. But anyways, you know that the tangential acceleration is the result as looking at the change of the velocity with respect to the time. Um, Obviously, that will depends, the value, and then the normal acceleration is calculated with a formula that was developed previously that is equals to the speed over raw, being raw, the distance between the path and the center of the path, so from basically the radius of curvature. That's what it is, and always acts towards the path center of curvature. There is an special case in which raw is not specified, and if that's the case, then you will have to be giving with some coordinates in order to calculate it, and that's a formula you usually use for such cases. So, how do we solve these problems? And I always try to put this in terms that it's a recipe and it works for all of the cases. But let's just read this. Use your normal and tangential coordinates when a particle is moving along a known curved path. Then you need to establish your coordinate properly. We were using x and y before. Now it's normal and tangential coordinate system. Then we need to draw the free body diagram and the kinetic diagrams. In this particular one, it's very important that we understand what we're doing. So the normal one points always inside or inward the path of direction, and then the tangential is always tangent to the path. All right, just don't forget that. And it could have a negative or positive t direction. Then after that, we need to apply the equations of motion in a scalar form, the ones that we just solved. Sum of forces in the normal direction are equals to mass and the normal acceleration. Then sum of forces in the tangential direction are equals to the mass, which multiplies the tangential acceleration. Always remembering these equations given in chapter number 12. So, as always, let's do an example. This is quite important, okay? So given the 10 kilograms ball has a velocity of 3 meters per second when it is at A along a vertical path, then we need to find the tension in the core and the increase in the speed of the ball. Okay? So what do we do? If we follow what we just learned, we need to establish an NT coordinate system so we can draw our free body diagram and kinetic diagram, and then after that we just need to apply the equations of motion in those directions. So if you have this, and I just wanted to, show you, right? You have your NT placed like this, and remember that usually the tangential or the x direction will always be established with the movement of the particle. This particle is going into this direction, therefore I specify that t will be positive into that direction. All right, and that's something to remember. Always that will be established, following the direction of the movement. If you don't do that, then you will get negative values, and that means that you assume the direction in the wrong way. Okay? Then you have your theta, which is equals to 45, and that will help you decompose all of the forces, such as the weight, which are not coincident with n and t, into the proper n and t. All right, so you will use that 45 with the weight in order to write your equations. So once you have that, and everybody's with me on this, we need to write the equation. So I will go ahead and write the sum of forces in the normal direction are equals to m that multiplies the normal acceleration. If we do that and we take a look at the free body diagram, we will see that we have the tension going up, right, in the positive direction minus the weight that multiplies the sign of 45 because it's the component of the weight into that coordinate system that I established, and this is equals to MAN. What we need to know here, and remember that AN, it's equals to the speed to the square divided by the by rho, which is the radius of the curvature, and that is given right here, as you can see. Okay, when I put those values in, I will get that this is 3 to the square divided by 2. Okay, and that will give me a number. Then I also have to know that the weight, and remember that, will be equals to the mass, which is 10, and that has to be multiplied by 9.81. And finally, we need to remember that the mass is equals to 10 kilograms. If I plug all of these values into the equations, I will get T minus 98.1 sine of 45, it's equals to 10 multiplies, okay, and when I do that calculation, I get that T it's equals to 114 newtons. All right, so that answered the first question, which is the tension of the cable. And now they are asking me the change on speed. Well, that's very simple because the tangential acceleration is defined as the change of the speed, which means that's what I need. If I do sum of forces in the tangential direction, I might get what I need. Sum of forces in the tangential acceleration or tangential coordinates are equals to the mass times tangential acceleration. That's what I need, right? So if I do this, the only thing I have is the weight that multiplies the cosine of 45, and this is equals to MAT. I have enough information to do this, therefore AT will be equals to 98.1 that multiplies the cosine of 45, and this is divided by 10. Therefore, I will get 6.94, I think, meters per second squared, and this is the same as dV dt, which is what they're asking me to find. All right, guys, this is very simple. I really consider chapter number 13 to be one of the easiest. It kind of refreshes everything that we've been working from physics 1 all the way until now, and that's why I don't see any problems on this chapter. However, if you have any issues, if you get stuck or something like that, I really encourage you to get in touch with me so I can help you more on a one-on-one configuration. All right. So that's it for this chapter. Let me know if you have any questions, and if you don't, I will see you in the next video. Thank you so much for watching.